folks. Welcome to another weekly episode of YFTT, Yugabyte Friday Tech Talks, a talk for engineers by engineers. Sorry about the delay. We had some technical difficulty in getting the feed out, but it's all good now. So, you're back to, we're in business. So anyways, let me jump quickly into it because we're a few minutes late. I have with me Sushant, and he's going to talk about how we've enhanced YSQL, YugabyteDB, which is based on Postgres, to show query latency histograms. Sushant, perhaps why don't you do a quick 1-minute intro and let's dive right in.
Yeah. Thank you, Karthik. Hi, my name is Sushant Mishra. I'm part of the query layer team at YugabyteDB. I've been with Yugabyte for a little more over 2 years. It has been really exciting, and we have built many cool features during my time here. And one of the cool things, the query latency histogram, is what we are going to talk about today. So let's dive right into it. So YugabyteDB includes a PG statement extension by default and uses this extension to track the execution steps of all the SQL statements. Now, specifically, once it comes to the latency, this statement tracks min time, max time, mean time, and a standard deviation time for the query execution, for every query. But there are kind of a couple of unanswered questions. Yes, we do have min and max, and also mean time, but we don't really know the exact distribution of the latencies of the query. And specifically, if we want to calculate the P99 or P90 latency for a specific query type, then that information is also not there, which is often very critical for the end users. So with that in mind, we added a new feature with following objectives. We wanted to keep track of the latency in different latency buckets for each query type. We wanted to provide a mean for returning the latency percentile for a given latency for a given histogram, and also allow users to configure the precision and resolutions of those latency buckets. And we will kind of really go over those in detail. I did link our public documentation for it, which contains more details. I'll definitely encourage everyone to kind of really take a look at the documentation as well for any further questions. So with this feature, we introduced a new column called YB latency histogram in the PG stat statement view. The type of this column is JSONB. And this column consists of a key value pair. And where the key is a latency range, and the value is how many times a query has been executed and took time in that particular latency range. And all the times are represented in the milliseconds, where the time spans are beginning inclusive and end exclusive. So just to kind of consider a quick example, if YB latency histogram has this value of 12.8, 25.6, colon 4, what it means is 4 times a query executed, taking between 12.8 to 25.6 milliseconds.
Got it. So let's understand that a little more, Sushant. So does this mean that, PG stat statement captures how many times a query executed, and now we are breaking down for that particular query, 4 of the executions had a latency in this window. Is that the way to understand it?
Yeah, that's correct, Karthik. Yeah, exactly.
And the units are always milliseconds.
The units are always milliseconds.
Okay, great. Fantastic. This is actually quite useful to know not just the average distribution, but the tail distribution. Yeah, this is fantastic. The distribution of the overall latencies. Yeah, keep going.
So let's take a look at this with a little bit more detailed example. So I created an example table foo, which has H as a primary key and another column V. And we insert some random 10,000 rows into this particular table, where the value of H goes from 1 to 10,000. Now we execute two specific queries on this table, where we select H comma V, where H is greater or equal to 1. So the interesting bit is we retrieve all the rows from the table in this particular query. And then we execute the same flavor of the query where H is greater or equal to 10,000, where we retrieve only one single row from the table. So as you can see, like when we retrieve H is greater or equal to 1, since we are retrieving all the rows, it probably should take us a little bit longer to execute in comparison when we are only retrieving one single row from the table. So this is the output of PG start statement after executing the query. As you can see, the number of calls are 2 for those corresponding to query execution. Min time is aligns with like when we retrieved only one query, one row from the table, and the max time aligns with when we retrieve all the 10,000 rows from the table. The most interesting fact is this YB latency histogram column, the 12.0 to 12.8 range contains one execution, which corresponds to when we retrieved only one query. And the second 19.2 to 20.8 contains the another execution when we retrieved all the 10,000 queries. So now we have like a distribution across the latency buckets to really show. I just kept it at 2 to kind of really show it clearly how it is getting locked. But you can imagine we could have like more latency buckets and different execution counts as well.
Yeah, this is fantastic. I think the 2 really clears up what is going on here. And one question for you, perhaps you're going to cover that. How did you get these magic numbers 12 and 12.8? So like the range 12 to 12.8 or 19.2 to 20.8, and perhaps that you can cover at some point.
Yeah, sure. So I will be covering that in a subsequent slide, Karthik. So we'll go over those, like what are these spans and the latency spans are.
Wonderful.
Excuse me. One quick point to note here is we only show the ranges for which the execution count is non-zero. So our histogram has like many other latency ranges as well, latency spans as well, but we don't really show them unless the execution count is non-zero. So it's just to kind of really minimize the unnecessary output and only really show the relevant output. So with that, also to answer Karthik's questions, what are the different latency spans we kind of really track? So we divided the whole time range into different latency spans, which we also refer to as the latency buckets. So 0 to 1.6 millisecond range is covered by the resolution of 0.1 millisecond. So basically 0 to 1.6 millisecond range will have like a 16 different latency spans, each covering 0.1 millisecond as listed in under the latency bucket column here. Similarly, 1.6 to 3.2, the resolution goes to 0.2, and there are total 8 different latency spans are there, each covering 0.2 millisecond. And it keeps every time we go to the next range, we keep doubling the resolution, and the time span covered also doubles up. These are the defaults, like when you use this feature. These defaults are kind of chosen as a balancing factor to giving the reasonable account of the query latency and the resource utilization. As you can see, maintaining all of this data requires extra memory and processing. So we wanted to keep a good balance between them. So that's where we kept these as defaults.
Got it. This makes a lot of sense. Yeah, totally makes sense. Let's keep going. Yeah.
So in this particular histogram, we track up till the max query duration of 167772 to 21.5 milliseconds, or we can easily say it's around 28 minutes. So if a query is taking more than 28 minutes, then it is recorded in something called an overflow bucket. An overflow bucket has a format of like, it shows you the max latency number of around 28 minutes. But after the comma, there is no end range here because that's the overflow part. And then again, as the other bucket, it records the execution time. So just for example, I executed this PG sleep one time taking around 7 milliseconds, and another time it's taking more than 30 minutes. And as you can see in the overflow bucket, this is recorded as one time. For the PG sleep when it took more than 30 minutes.
Makes sense. Yeah, makes total sense. And the last bucket is from that to any amount of time, right? Like, so everything will be lumped because that's already a very long period of time. It is 1600 seconds, right? So
yeah, 1600 seconds. Yeah. So yeah, it's a very long period of time. I generally don't expect queries to be taking longer unless there's a very long running command. So
makes sense.
Moving on to the next part, right? Some users might want to really configure this various factors like the resolution and other factors with it. So going over those, so we introduced a configuration called pgstat_statements.ybsdr bucket factor. And its valid values are 8, 16, and 32. Current defaults, as I noted earlier, is 16. So what it does is it kind of really tracks what is the time span for very first interval is, which is tracked at a resolution of 0.1 millisecond by default. So for example, if we choose a value of 32, then previously by default, 0 to 1.6 was covered at 0.1 second resolution, and you get like 16 buckets, 16 latency spans here. But if you choose a value of 32, then your time span doubles up, it goes up to 3.2. So 0 to 3.2 is tracked at a resolution of 0.1 millisecond. So basically, we just increase the range, which is tracked with a resolution of 0.1 millisecond. Now, one point to note is here, this actually specifies the number of latency spans for the very first one. The rest of them are just derived based off of that. So rest of, and even in the previous example, the first was 16 and the rest of them was 8. So in this case, the first we are specifying as 32. And the rest of them are half of that. And like every other one is 16. That's just because of the specific implementation detail. So so by changing this, we can kind of really control like the whole histograms of all the latency spans. Beyond that, we do have plans for adding 2 more configuration variables. One is the latency resolution of the buckets. So for example, this time span of 0 to 3.2, if we want to kind of track at, let's say, either a higher or lower latency resolution, let's say instead of 0.1, we want to track it at 0.2, then users should be able to change that as well. And the last one configuration is the max latency range. So as we talked about the max latency range, we are planning to track is around 28 minutes. So that we are also planning to make it configurable. So if some users want to kind of really increase that to a higher value, then they can do that once that is available. So both of these changes are tracked by this GitHub issue, which will be available in our some future releases. So now to the most interesting part of this. to solve the objective of getting a percentile, we introduced a function called YBGetPercentile, which can be used to find the percentile. So what this, for this particular use case, it can take a input of YB latency histogram and the target percentile as an input. As you can see, it takes the input as a histogram, which is of type JSON-B, and a percentile, which is of type double. So just to kind of go over a quick example, so I pass this function an explicit histogram of different latency ranges, and then the target percentile, 99, and it gave me a return me the P99 latency of 3.6 millisecond. And similarly, in the next example, we pass the percentile as 90, so it gave me the percentile of 2.2.
Makes sense. I think this is fantastic. Yeah.
Sorry. So let's try to get like a more practical example using the PG stat statement. So excuse me. So we are so this particular query tracks many different execution stats from the PG stat statement for a specific query which I was executing, and simultaneously calculates also calculates the P99, P95, and P90 latency using the YB latency histogram. And as you can see, the mean time, which is kind of almost the average time here, is 21.4, and we can see the P99 is 28.8 milliseconds, P95 is 24 milliseconds, and P90 is 22.4. So from this, we can correlate like the P99 is much closer to the average latency in this particular example, and we can kind of really configure it to kind of really have more different kind of a percentiles calculated as the end user desires. So when we introduce this feature that so as a part of this feature, when we introduce a new column, which requires this extension PG stat statement to version that 1.6-YB-1.0. This extension can be manually upgraded using alter extension command, though this command is required to be executed in each database cluster.
So let's clarify that, Sushant. Are you talking about each database, logical database, Postgres database in the cluster, or each physical universe?
Each logical database in the universe.
Got it. So you have to connect to every database and you have to run this command. And because the upgrade is one per database, I'm guessing, right? Like the version is specific database. Got it.
Yeah, that's correct. Yeah.
Got it.
The self-managed YugabyteDB cluster can be upgraded by the process listed in our docs. Basically, it's about executing just one command, which upgrades all of your system catalog and also the extension. For YugabyteD cluster upgraded using YugabyteD Anywhere, the PG status test extension is upgraded as a part of the upgrade process automatically. So there's no further action is really required. One critical point to note here is, and this is where we differ from the Postgres. Whenever the in Postgres, or whenever the new column is introduced, then after the upgrade, the previous stored stats in the PG stat statements are dropped. But in case of the Yugabyte, for better debuggability, we actually retain the stats. So if you upgrade the extension, your previous stats are also retained as is. They are not really lost. It's just that like there is a new column which is added, which initially will not have any data populated in it.
Got it. Makes sense. Awesome. So perhaps you have a demo for us? But oh, you got something else. Go, keep on.
Yeah. So just to very quickly talk about like this feature is available in 2.18.1 release onwards. The YB percentile function is available starting from 2.18.2 release. And just as a final note, we also have this integration of the latency histogram and percentile in Yugabyte anywhere as well. And I linked the documentation pages for that, so you can refer to them for more details on that. So let's go to the demo part of it.
As you're bringing that up, Sushant, Amit says that this new histogram column is fantastic. It's a fantastic ad. It'll make troubleshooting so much easier. So yeah, totally agree. And thank you for this session.
So going over the demo, I just want to give a quick overview of like what we are kind of going to be doing in the demo. So I created table foo, which has H as a primary key, and then we have some 3 more integer columns. And we again generate 100,000 rows in this particular table with some random data. In terms of the workload, the following transaction get executed. So we start a transaction, and the first thing the transaction do is it locks the very first row where H is equal to 1. So this for update is actually the syntax for locking this particular row. So once the row is locked, like there's no other writers can come in, like they have to really wait behind this particular transaction. And once the row is locked, then we update V1 column, just increment it by 1 for that particular locked row, and then we commit the transaction. So what I do in my demo is I run it for 120 seconds, and I only launch 5 concurrent connections, and all of those concurrent connections are doing this particular transaction.
So heavy contention, right, in this case?
So very heavy contentions. Yeah. So all of the 5, so just to kind of make it a little bit more clear, that all 5 connections come in and try to acquire the lock when
the same row
for update.
The exact same row. Yeah, makes sense. Yeah,
that is correct. Yeah. And so one transaction will win and another 4 will wait. And that kind of really causes the variability into the latencies for different transactions. Like which transaction wins first versus which transactions really wins last. So with that, I'll switch to the demo.
Yeah.
Right. I have everything kind of really hard coded. I just ran it here. So this is the table foo which I just described. And I started this workload while we were just going over the schema.
Okay.
Using a script. And all of the details for running the workload is captured in this particular output file.
Got it.
So I'm running this workload using the YSQL bench, which is also AKA known as PG bench in the Postgres world.
Yeah.
So as you can see, I ran this workload for 2 minutes, and we get on an average, I'm displaying the stats at every 10 seconds. We get around like 197 transactions per second with the average latency of 25 milliseconds. And that's on the client. As I mentioned, I launched like 5 concurrent connections. Now let's take a look at like what is our stats are for the select for update statement. So this is the select for update statement. Sorry, right here. This is for the select for update statement. So the mean latency was 25.5 milliseconds, and P99 is 28.8, P95 is 24 and 22, and P90 is 22.4. And you can see the most interesting bit is like, as we can see here, like few executions actually went over even 50 milliseconds because they just couldn't really get in. Other transactions were holding the lock. But most of the transactions kind of really finished around in this up till this particular bucket, and that's where we kind of really see the P99 as at 28.8 milliseconds. And also just sorry.
No, I said fantastic. This is really awesome. Yeah, to see this level of detail.
Now, just to kind of really quickly look at the next statement as well, the update. Since once you already have the lock, then the update is supposed to be very quick, and we can see like the average time is like very low, 1.78 milliseconds, and P99 is 3.6, and correspondingly P95 is 3, and P90 is 2.8. And you can also see is like there is one outlier here which took pretty long, beyond 8 milliseconds, but most of the executions are up till right here, right? So as you can see, like majority of the execution for this particular update finished in very reasonable time. That's why we kind of really see much more reasonable P99 latency.
This is fantastic. Clearly explains what's going on. Yeah, this is amazing.
So I wanted to just show one more thing in the Yugabyte anywhere, and that's why we kind of really see. Sorry, did I have a question on that call?
No, I think it's just
okay.
Something like.
So this is our Yugabyte Yugabyte managed, where we as a under the queries for the slow queries, we capture the PG status statement collected from all the nodes. This is the query specifically for the select for update, which actually tries to log the particular query. The interesting bit is like in our Yugabyte managed page, we automatically calculate the P20, calculate and show P25, P50, P90, 95, and 99 latencies. And if you click on the details, then you can see like further more stats are related for the PG status statement. So if you are using the Yugabyte managed, then everything is kind of really available directly in this page. And this also aggregates the data for a particular query from all the nodes and show you the aggregate. What I was doing is I was just connecting to one node and showing the data from there. But this particular page shows the aggregate from all the nodes in the YugabyteDB cluster / or Yugabyte universe.
Fantastic. This is amazing. Yeah.
All right. So yeah, that's all for today. Hopefully folks like this feature and hopefully it will help them to troubleshoot their various query latency issues.
Yeah, thank you, Sushant. I know I loved that feature, though. That was amazing. Hope you guys enjoyed it too. Once again, please feel free to drop any questions you have in the LinkedIn comment box. You can join our Slack. There's a URL right there, yugabyte.com/Slack. Head to the YFTT channels. We'll be looking for questions there as well. And remember that we have another DSS, same place, same time next week. Sorry, we have another YFTT coming up in a couple of weeks. Next week is our flagship event, the Distributed SQL Summit. It's the 5th time we're running it. It's the 5th annual event, the 5th time we're running it. A lot of amazing talks lined up. Please feel free to join us. This is on Tuesday. And Lauren has dropped in the LinkedIn comments with the URL to register. Hope to see you guys there. Thank you for joining us. Thanks a lot. And Piet says, thank you. This can serve things like SLA reporting as well, which is absolutely true. So thank you, folks.